Welcome back, AP. New chapter, a new day. We're going to start learning about not only gases, but their behaviors, gas laws, and how do their motions get affected by changing certain variables. So, in 10.1, characteristics of gases. Gases are shapes, they're not definite. Okay, their volume not definite is because they can spread out throughout that whole entire container. The spacing is very, very, very far apart. Gases are not interacting with other gases. They're basically colliding off of each other, and they're constantly moving. Now, you can make particles move faster or slower, but they are constantly moving. Diffusion, we're going to get to diffusion when we get to about, I believe it's 10.8. Very, very fast diffusion. And all homogeneous. So whether you put O2 or some CO2, when they come in, gases are always homogeneous. Okay. Compressible. Out of the three states of matters, gases are the only ones that are compressible, and the reason why you know that is balloons. They have huge empty spaces between them, and when you bring these particles closer together, you can compress them. You can't do that with solids and liquids. You just got a mess. So we know gases are compressible because we can move and put pressure on them to bring them closer together. So we're going to analyze that when we get to the very first gas law in the next video, Boyle's law. Density is making a big appearance, and I want to say it's around video 10.4 or 5. Density for gases, they're very low, and that should make sense because gases, majority float. Majority float, not all of them float. When we do the calculations for gases, we will be using grams per liter. Be very careful when we were doing density for liquids. For liquids, we were using grams per mil. And the reason why we use liters instead for mils, because we're talking about larger amounts of particles. So we got to make sure that we have the correct units. 10.2, let's first talk about what the heck is pressure. All gases exert pressure on their surroundings. So whether you're looking at a box, a beaker, a balloon, okay, all gases exert pressure on their surroundings. So you not only have pressure inside the container, and we draw these little arrows to represent this pressure, but also you could put pressure on the container, okay? So it's a force that exerted by gas molecules as they strike the surface around them. So not only the surface of the container, but basically the surface with each other. We're very familiar with a lot of gases, especially what's in our atmosphere, nitrogen, oxygen, CO2, argon. We've heard all these gases before, but together they exert what's called atmospheric pressure. Atmospheric pressure on us and the earth. So what keeps us on earth is gravity, but there is a force, there is a pressure that's keeping us also down. It's that gravity force. So pressure is a force just like gravity is a force. So atmospheric pressure on us, and how do we measure atmospheric pressure? We measure it with a barometer. Okay, some people call it barometer, barometer, but anytime you ever hear the weather people on the news channels or on the radio and they're saying the atmospheric pressure is very high or low, well, they have a barometer, which I also have one on the wall in my classroom. I'll show you. And inside that barometer is filled with mercury. And that mercury level, mercury has an inverted shape of its meniscus. That level will either go up or down depending on that force that's acted on it. The barometer was invented by a scientist named Torricelli, and we're going to look more into what a barometer is all about. Inside here, this kind of little sketch that I got, if the tube is filled with mercury, so this right here is that mercury, and then you have like what we call a pool of mercury. If that tube is filled with mercury, that pressure from the top of the mercury down to the pool, that pressure, either you put pressure on the mercury, which makes the mercury level go down, Or is the pool of mercury putting pressure on the mercury to make it rise? So if a tube is filled with mercury and then inverted into the container of an open atmosphere, okay, key is an open atmosphere, the mercury will rise to 760 mm up the tube. Now mm, millimeters. So we're measuring distance on how high or how low that mercury travels up that tube. At sea level, okay, so the ocean, the atmosphere pushes the mercury 760 millimeters up the tube. So we actually have a standard number for pressure, and it's called 760 mmHg. So millimeters of mercury. So that is standard pressure, and that's standard atmospheric pressure, and we have an abbreviation for atmospheric pressure. It's called ATM. So 760 mmHg equals an atmospheric pressure. So anytime you listen to the weather people, when they're talking about pressure, they're talking about how much pressure is in the air. If there's a lot of pressure or if there's low pressure. There's two factors that can actually change atmospheric pressure, like altitude. Whether you go into the mountains, so higher elevation, or whether you go to like the ocean or even just Fontana, higher atmosphere, there's smaller amounts of air that's above you. So the atmospheric pressure is very low, which means if you actually read the pressure up there in the mountains, it's less than 760. But here at Fontana, the ocean, we have greater atmospheric pressure. So that barometer is actually going to read greater than 760 mmHg. Okay? So whether you change altitude, that can change pressure. Weather, okay, especially weather. Oh my goodness, if you've ever been in like humid conditions, like the tropics, southern states, there's a lot of water molecules in the air. So that means our atmospheric pressure is greater, and that's why when you go outside, you had nice, pretty straight hair, and then as soon as you go outside, and it's all nice and frizzy. That's because more water molecules are in the air, and the pressure of the air is greater. In drier regions like the deserts, Palm Springs, humidity is very low because there's not a lot of water molecules in the air. So the pressure is very low. So depending on altitude versus weather, that can change pressure. I posted a little video on Teams, the history of the barometer. It's a YouTube video, a TED Talk. I'd like you to write down 5 facts that you learned about the history of the barometer. Okay? After you watch that video, then continue on to our next example. Let's draw what a barometer looks like. Okay? A little sketch. So, notice we mentioned the word open. Open atmosphere. Okay, so we're going to draw 3 pictures. So one of them is going to be open, where we actually have the pressure of the gas is actually greater than the pressure of the atmosphere. So I'm going to call this picture number 1. And then, like I said, we're going to draw 2 more pictures. So a barometer, it's got this little tube of gas. So we call it pressure of gas. Now, who that gas is, it doesn't matter who the gas is, but it's a tube, and it has this U shape to it, just like this. Okay? And then right here is the open end to it. So, because it's open, I actually have pressure coming in, and we call this atmospheric pressure. So we call it P and then little ATM. So this is the air pressure that's coming in. And then inside of here is mercury. Now, if the pressure of the gas is greater than the pressure of the atmosphere, that means the pressure that's being exerted in this tube is pushing the mercury closer to this open end. So maybe shading this in, this is all my mercury. And obviously draw way better in the lines than me. So because the gas pressure is greater than the atmosphere, that pressure of the gas is actually able to push the mercury closer to the opening. Okay, so we actually measure this height difference. So we call this P little h. I don't want you to think pH is like acids and bases. This is P little h. So I'm going to make a little note. P little h, it's the height difference of the two sides of mercury. Okay? Now, this value is always positive. Okay? Always positive. So the height difference, you just subtract the tall side versus the small side. Okay? The units of this, so always positive. We're going to use mmHg because we're talking about millimeters of mercury. If by chance AP gave you centimeters, nothing wrong with that. Use a little King Henry. Okay? So because that pressure is higher on the gas side, we have an equation called pressure of the gas equals P ATM, and we add it to the pressure of the height. Because remember, this value should be larger than this P ATM. This should be a smaller value. So when I add these two values up together, I should get the pressure of the gas. So we have this equation. Okay? You can use any pressure units you want. And right below, we're going to talk about the different pressure units. But for right now, we're just going to use mmHg. Okay? Well, so use any pressure units, but as long as they're all the same units, because you're adding. Okay? You have to have the same units when you're adding. Okay? So the key is that it's open and the pressure of the gas is greater than the atmosphere. Okay? So now where do you think we're going next on scenario number 2? Well, let's keep it open. But now let's say the pressure of the gas is actually less than the atmosphere. Okay? So we're going to draw our U-tube shape. And we're going to say the word open, always label open. And my P atmosphere that's coming in, the air pressure that's coming in, is actually so great that it can actually push the mercury closer to the gas. So now instead of the shading being higher on the right side, actually my shading's now going to be higher on the left side. Okay, so maybe it's about like right there. Okay, so my pH, same thing. pH, it's that height difference. Okay, even though this side is higher than that side, it's still a positive number. Okay, so now in this case, I know that my atmosphere is going to be a greater value. So my P gas, P ATM, and pH. Instead of adding, we're actually subtracting. Because remember, this value should be a smaller number, less number, and my PATM is a larger number. So a large number minus a positive value, that means this P gas is going to be a less value. So in one case you're adding, the other case you're subtracting. Okay? So now the third scenario. We've mentioned that it's open. Well, what happens if it's closed? Okay? And it doesn't matter which picture you use, picture 1, picture 2, because basically it's like you're putting a stopper. You're covering it up. So that right there is now stopped up. That means there's no pressure, PATM, coming through. So whether your mercury is higher on the left or the right, doesn't matter. Because, oops, I went too much on the shading. There you go. Okay, and I'm going to put right here, or vice versa. And then P gas. Okay. What happens is you took this part, P gas equals, and because I shaded it the same as picture number 2, PATM minus pH. Okay. You took that part completely out. Okay. So doesn't matter that it's added or subtracted. Your P gas is going to be whatever the height is. So once you determine that height is the pressure of the gas. So like I said, that little minus sign doesn't matter. I don't want you to think one's positive and negative because, and make sure you write this, pressure is always positive. It's a force. You can't have negative pressure. You either have pressure or you don't. Okay? So, number 1, know the 3 scenarios. Okay? Know the equations. Okay? And then be careful, know how to draw the barometer. Which side, higher or lower? And fourth, most importantly, the math, the sig figs. Because you're adding and subtracting, be very careful, the least after the decimal. Okay? Know the equations, and I'm going to go back to number 2, make sure you have the same units to add and subtract. Okay? So let's do an actual scenario. The book gives you a couple, but doesn't give you a lot. It's not a big topic in AP, but you do need to know how pressure is measured. So in a lab, we have a barometer, and it says that the atmospheric pressure is 764. So let's get those calculators out. So that's my PATM. All right, bust out those calculators. I know my barometer is going to have this basic picture. So we have to figure out what the scenario looks like with that mercury. So I know this is my pressure of my gas, and I know that's PATM, which they just told me PATM was 764.7 torr. Now torr is another pressure of units. So like I said, I'm going to get to all the different units, but that's just another pressure. A sample of gas is placed in a flask, so I got gas in there, and it says open end, so that just told me a lot of information. And that PATM, that means it's able to go through the tube. The height of the mercury in the open end is 1.364. So on the open end, I know I have 136.4 mm. Remember, mm, Hg, this is mercury. And the height of the arm that's in contact with the gas, so over here, is 103.8. The open end has a higher height than the arm connected to the gas. So I know my mercury is higher on the right side than it is on the left side. Let's do a little bit better coloring job than that. Okay, so that pH right there, I'm going to take the difference. Well, I got to show that work. So pH 136.4 mmHg minus 103.8. So when you're subtracting, I do have one number after the decimal. So when I subtract, bust out those calculators, we should get 32.6 mmHg. Okay? So now we go back to our scenario. Which equation am I looking at? So I know it's P gas is PATM and then pH. The question is, am I adding or am I subtracting? So because the pressure is higher on this open end, that means that the pressure of the gas must be more powerful to push that mercury closer to the open end. So that means my P gas must be greater than my atmosphere. And let's check above. So if the pressure is higher on the right side, and there it is, that means I'm going to be adding. Okay? So that's the scenario that I'm looking at. I have torr for my open. So my pressure ATM is 764 torr. But I have mmHg. Well, let's take a little gander about units. Pressure SI units. SI units, Pascal. This is the units that we use to communicate in the world. So when we talk about pressure from one country to another, we got to make sure we're talking about a Pascal. Okay? And you would think atmosphere would probably be the SI unit of the world, but it's actually the Pascal, after a scientist named Pascal. And you'll hear about him in the TED Talk video right above. So Pascal has an abbreviation of capital P, little a. But there are other important units. Well, there's ATM. Torricelli, he even has his own unit. I mean, why not? He's the one that invented the barometer. So we call it torr. Millimeters of mercury, there's the one we've been using. Because Pascal can be such a big number, we also have kilopascal, little k, capital P, little a. And then if you've ever put air in tires, well, you have what's called pounds per square inch, okay? All of these units relate to each other. So it's kind of like moles. 1 mole equals molar mass. 1 mole is Avogadro's number. Well, they all relate to each other. So 1 ATM is 760 mmHg. And remember what we set up here in the picture, standard pressure 760 mmHg is 1 ATM. Okay? Well, mmHg is the same as torr. They're both the same value. Okay? Well, that makes it easy. A Pascal equals 1 ATM, but it's a huge number, 101,325 PA. Kilopascal, because remember, I can even put Pascal in my King Henry box, and then I have kilo, hecto, and then deca, so I got to move it 3 places. And then PSI, 14.7 PSI equals 1 ATM. They all equal each other, but they're all equal to 1 ATM, okay? So that means I got to take these torr and I got to get it into mmHg. Well, you set up a little conversion. To get rid of torr, 760, and there's 2 sig figs, and mmHg, 760. Well, I hope, ladies and gentlemen, we're not looking at a calculator, because 760 divided by 760 is 1. So that means 764.7 mmHg. Now I know you're probably thinking, wait a minute, what about sig figs? They had 2 sig figs. I didn't need 760 in the calculator. I didn't even need it for the calculation. I just needed to change the unit. If that number would have been different, well then yes, we actually look at the sig figs. So I'm going to base my sig figs off that starting number. So 764.7 mmHg. So now I have, from above, I have my atmosphere. So P gas equals the atmosphere, which we just found. So that is this guy, 764.7 mmHg, added to the pressure of the height, 32.6 mmHg. And because they each have 1 after the decimal, so let's plug and chug that in. So pressure of the gas looks like about 797.3 torr, or sorry, mmHg. Okay? We found the pressure in mmHg, but notice what the problem said. What's the pressure in atmosphere? And what's the pressure in torr? Well, I guess I probably should have kept that in torr and then just changed this guy into torr. Doesn't matter. That value is the same value, 797.3 torr. And how do we know? Because they equal each other. Now if I want to go ATM, because it says right there, what is it in atmosphere? So pressure of the gas is 797.3 mmHg. Well, look right there. 1 ATM is 760 mmHg. I put that on the bottom. And 1 ATM. Bye-bye mmHg. Okay? 760, we don't use this for sig figs because it's a constant. We base our sig figs off of this 797.3. If by chance you forget that concept with the sig figs, not a big deal. It's kind of like the moles. We don't use the moles for the sig figs either. So 797.3 divided by 760. So I'm going to get 4 sig figs, 1.049, and then ATM. So that's how we convert from one unit to another. So let's do a couple practicing with converting units. So let's say problem number 2, I have 657 mmHg and I want to go to torr. Okay, so it's right there. And conveniently enough, they equal each other. All right, so 657 mmHg is the same thing as saying 657 torr. Don't need to show any math because they equal each other. Okay. What if I have 830 torr and I want to go to ATM? Simple one-step conversion. So for torr, 760 torr equals ATM. So 760, 1 ATM, bye-bye torr. And then I'm going to divide, and I'm going to go 2 sig figs, so I'm going to get 1.1 ATM. And then make sure you box that answer. Okay. Let me go over here so that way I can keep my little screen over there. I have kilopascal, and I want to go to ATM. So 7.8 kilo, make sure that P is greater inside. And kilopascal, 101.325 equals an ATM. So 101.325, little k, big PA, and then 1 ATM. Okay? I'm going to use my 2 sig figs. So when I divide 7.8 divide 101, I'm going to get 0.077 ATM. Okay? So it's just like when you calculate, ladies and gentlemen, grams to moles. You're just doing a conversion. So 1200 PA, Pascal, and I want to go to mmHg. Well, this time you're actually going to have 2 values, top and bottom. We've only had just one value on the bottom and just 1 ATM on top. So for Pascal, 101.325, and I want to go to mmHg. Well, Pascal, big number, and mmHg, 760. So you do have to put both values. So I'm going to multiply and divide. So bye-bye Pascal. It looks like I'm going to do 2 sig figs. So plugging this in, and I'm going to get 9.0 mmHg. Okay? So that's the history of pressure. That's how we use the units of pressure, and these are the 6 different units of pressure we're going to use throughout this course. Now, you know I hate that word memorize, but you got to learn that conversion. Okay, what does an ATM equal? An mmHg, torr, Pascal, kilopascal, and PSI. Okay, see you on the next one.